The central focus of what I'd like to talk about today is the performance and benefits of opening both ends of a submerged module to filtration, or double ending. But in order to do that, I'd like to review what is attractive about a submerged membrane system and where the innovation opportunities are. I'd then like to talk about what has traditionally been a limitation for submerged, which is the available pressure range, and why pressure losses are so significant. I will then talk about how opening both ends of the module to filtration can reduce these limitations, both in theory and with the results of a controlled trial of single versus double-end filtration. And then I'll spend a little bit of time on the financial implications for double-ended filtration. The low-pressure hollow fibre membrane market is broadly broken up into two categories, pressurized and submerged. The differences between submerged and pressurized and the advantages and disadvantages of each is a whole presentation topic in and of itself. But there are certain applications where each of the systems is most competitive. They're sweet spots, so to speak. The applications that are sweet spots for submerged are firstly filter bed retrofits. The filter beds can be repurposed as submerged membrane treatment cells. This is an important advantage in that it offsets the cost increase in upgrading to a membrane treatment method. Secondly, submerged systems are typically less energy intensive, primarily because of the differences in how submerged and pressurized filtration pumps are set up. Submerged systems are also at an advantage in countries where the labour and construction costs are low. For pressurized systems, there is a higher proportion of construction done at the manufacture of the pressurized unit, whereas for submerged, the higher proportion is the cell construction at the site. So when plants are being installed in countries where labour and construction costs are lower than the country that manufactures the membrane systems, there is a clear advantage for submerged. And finally, for low flux applications, like those with coagulated feeds or high turbidity, which typically will require low fluxes, submerged is a good option. Low fluxes normally mean more membrane modules are required. When you scale up the number of membranes required in a pressure system, the increase in costs is largely proportional because more membranes means more pressure vessels. On the other hand, for a submerged system, the difference between building a concrete tank for, say, 1,000 modules is actually not a huge amount more expensive than for 300 modules. So clearly there are applications where submerged systems offer a good option. For suppliers to remain competitive, they need to continue to invest in submerged development. I've been involved in a lot of membrane development projects over the last 18 years. While each project is unique, the types of developments fall into three broad categories. In general, the safest and quickest investments are in improved operating protocols. For example, what is the optimal backwash flow rate? What kinds of maintenance cleans are beneficial, and so forth. The aim is to reduce energy and chemical costs and prolong membrane life. There is a reasonable amount that can be done in this area, but performance is limited as the intrinsic properties of the actual product don't change. So then there are changes to the actual product. So firstly, manufacturers can look at the module design. So I'll go into more detail on what those changes could be in just a moment. But these changes are centered around how to put established membranes into different module envelopes. For example, when Evocor first launched the CP pressurized product, they used an L10 module. But then they were able to achieve cost reductions by developing the longer L20 module. The biggest gains here for the final product are in cost reductions through improved manufacturability or footprint reduction through smarter space usage by modules. This comes with a bigger investment risk because it involves changes to manufacturing processes and requires significant performance validation time to ensure that the changes don't affect the product hydraulics. And lastly, there are changes to the membrane fibre. This is the biggest risk because fibre changes really get into the science and discovery side of things. An example of this is the N fibre currently used in Evocor membranes. The investment made to launch this product, from lab-scale formulation development through to investment in manufacturing equipment and large-scale validation, was a much bigger investment than that L10 to L20 change. So I want to concentrate on the first of these two bubbles because operating in a double-ended configuration takes in a little bit of both of these areas. So what can you do to change the design of a module? Module length changes are highly desirable in submerged systems, not the least because filter bed retrofit opportunities generally come with nice deep tanks, and being able to use that depth has distinct cost advantages. But a disadvantage of increasing length is greater head losses in the system, which I'll go into more in a moment. So module geometry is another option. So for example, changing a round module into a square module, or expanding the circumference or the width. You might change geometry to help you pack more membrane into a tank, or to improve the handling or manufacturing processes. So for example, the Memcor CSII was launched recently, and it was a fatter module than the previous pressurized product, the CP. And then lastly, you can experiment with changes to the number of fibers that you can pack into a module. So whether that is through changing the diameter of the actual fiber without formulation changes, or through fitting more into the same module space. Now these last two options come with more risk because they change the properties of the membrane pots and the manufacturing processes and potentially the hydraulics of the module in operation. The length changes, on the other hand, on their own will come with no changes to the module pots, so there isn't much change to the manufacturing processes. So let's concentrate on increasing length for a moment. I've shown here the HAGEN-POISEUILLE equation for laminar fluid flow through a pipe. So delta P is the pressure loss or head loss of the fluid as it flows through the pipe. When the flow is in the laminar region, the pressure losses are proportional to the flow rate of the fluid, the viscosity of the fluid, and more importantly for our discussion here, the length of the pipe. And it is also inversely proportional to the power of 4 to the diameter of the pipe, which has effects for some of the other module design changes we talked about, but we won't go into right now. Now when we apply this equation to membrane modules, where we can equate each membrane fiber to a pipe or a small pipe with water flowing through it, for the same amount of flow through a fiber, the longer we make the module, the more pressure we lose in operation. And this here is one of the key limitations for improving submerged filtration. So the biggest limitation to submerged is that it is a suction-driven or vacuum process, and the pressure losses in the system from all the factors combined, including most significantly the pressure loss across the filter cake of a dirty membrane, and now the pressure losses due to the length of the membrane fiber, are limited by absolute vacuum. So when you get to the limit of your available pressure range, you need to clean your membrane fibers. Nobody likes cleaning membranes. It represents plant downtime and chemical costs. So minimizing the pressure losses from the fiber length is imperative. So I'm showing here a membrane module. In a single-ended membrane module, the filtrate comes from the top end only. So for a module of length L, the pressure drop is proportional to the entire length of the module, as shown by the dotted line in the graph. This has been the greatest challenge to improving the cost position of submerged by increasing the length. The pressure losses of a longer single-ended module would increase significantly the system pressure losses. However, when you take filtrate from both ends, that is, you make the module double-ended, you're effectively placing two pipes on top of each other of half the length of the module and losing pressure only half of that length, as you can see by the solid lines in the graph. This is because the filtrate will only travel to the closest pot, which is a maximum of half the length of the module. So this reduction in pressure losses by double ending means that theoretically the system operates at a lower pressure difference and has a longer time between cleans. So the question is, does this translate to actual membrane practice? We've talked about increasing module length. We've talked about double ending modules, but we've also talked a fair bit about the risk associated with product development and creating new manufacturing lines. So the industry as a whole has taken a position against risk in recent years, and increasingly there have been strict experience clauses in bid contracts that mandate previous experience in both the number of plants and the size of plants that have already used the new product. There are good reasons for this, but it can have the effect of slowing down the ability of larger plants to access the latest innovations. So we believe the answer to this is the L20N product that I mentioned earlier from Evoqua's CP product range. For Evoqua, submerged plants have used the S10N module. This is a single-ended module, a little over 1 meter long. The L20N module, on the other hand, is 50% longer and is double-ended, but it has been used in pressurized systems. Now, both of these modules have the same diameter, and both have been used extensively throughout the world, with over 30,000 modules of each in operation. As the modules are the same diameter, it is quite feasible that with a small amount of change to the submerged system setup, which is really just an engineering exercise, that Submerged can be operated in a double-ended configuration with an established product. So before we get into the application of the L20N, let's take a quick step back to the HAGEN-POISEUILLE equation. So on this graph, the top grey line represents the theoretical pressure loss down an S10N fibre at different operating fluxes as predicted by the equation. The blue line shows the pressure drop for the L20N module. So theoretically, as shown by the bottom line, the pressure loss difference is between 4 and 9 kPa depending on the flux. For a 60 kPa operating window, for example, this is a difference of 6 to 15%. Over the lifetime of a plant, this is a significant difference. There are several reasons why it is advantageous to apply the L20N module to submerged systems. Firstly, it allows double-ended filtration, so it reduces pressure losses. This opens Submerged up to the longer module, in this case 50% more length, which brings a 50% increase in filtration area for the same plant footprint. But at the same time, it utilises more of the filter bed depth in retrofit situations. It has the same module diameter as an S10N module, so the hydraulics around removing any solids that are entrained from the centre of a module are not changed. But it also means that the system engineering changes are reduced because much of the submerged componentry can be reused, which is good news for owners of S10N plants wishing to increase the capacity of their system. And not the least important is that the performance of the membrane itself in terms of fouling resistance, cleanability and flux capability have already been demonstrated in both pressure applications and submerged applications because the membrane in each module is the same. But there is a reason that this hasn't been implemented long ago, and that is because there is one key challenge to double-ending a submerged membrane, and that is the backwash. So the backwash relies heavily on the introduction of air from a blower to remove filtered solids from the fibre surface and from within the module. In a single-ended submerged system, the bottom potted end seals off the membrane fibres and the backwash air is introduced underneath the module. The membrane fibres are oriented in the vertical direction, and introducing the air at the bottom of the module ensures that the air is used efficiently from top to bottom as it rises to the surface. If that bottom end is now repurposed for filtration for double-ended, the air needs to be delivered differently. So our aim then was to prove the concept on real products. This was done at a place we called Memcor, which is our product testing facility outside of Sydney. We took 2 pilot units that were previously used for piloting with single-ended S10N modules. In one of those units, we put an S10N module as a control for the test, and on the other, we increased the tank height and provided a means of collecting filtrate from the bottom in order to allow the testing of an L20N module. So the same flux was used for both forward filtrate flow and backwash reverse flow for each unit. And there was no need for program changing as we operated in the same filtration and backwash protocols of our normal single-ended submerged operation. The standard backwash protocol is an aeration step to loosen solids followed by the introduction of liquid backwash. The solution to this is relatively simple. A low-cost aeration sleeve was developed to surround the module pot and deliver the backwash air adjacent to the bottom pot. A thin, non-pressurized containment shell attached to the aerator then ensures that this air is kept in close proximity to the membrane fibres it is cleaning, so as to maximise the efficient use of the air, and it facilitates lower airflow rates as well. So you can see that here in the parts shown in a grey-green colour. Down the bottom we have a sleeve with aeration openings around the periphery. The feed source for Memcor is South Creek, which can be quite challenging despite its picturesque outlook. The creek is 64 kilometres long and is subject to urban and farm runoff. It in fact forms the boundary line for several highly populated suburbs. The runoff from these areas brings nutrients, sediment and heavy metals. There are also 3 sewage treatment plants upstream that feed into the creek, which during dry weather form a large percentage of the creek's makeup. It is highly turbid and we see very large changes in turbidity during rain events. But all of this is fine because in our instance we really want to challenge our membranes so that we can develop products that we can confidently say can handle tough conditions. The highly variable nature means that we encounter a variety of test conditions as well. I'm showing here a graph of the feed temperature and turbidity levels during the period of our test. The feed temperature, as you can see, doesn't fluctuate greatly and is quite mild. The feed turbidity, on the other hand, is quite high and quite variable. At the most challenging part of the test, the feed peaked at 500 NTU. I mentioned earlier that the fluxes were the same for each module. For this test, they varied between 50 and 75 litres per metre squared per hour. And as you can see from this image on the right, apart from length, the dimensional attributes of the membranes didn't change. There is one exception to all of this, and that is the aeration flow for backwash. An initial period of testing showed that not as much air is needed during a backwash when using the double-ended mode in order to remove the filtered solids. So for the trial in question, the S10N used approximately half a metre cubed of air per 1,000 litres of water produced, as opposed to the L20N, which used only 0.4 metres cubed per 1,000 litres. And here are the trial results. Let's take a moment just to describe the graph. I'm showing here the TMP on the left, which is applicable to the blue and red traces. The blue trace is the TMP across the membrane for the single-ended S10N module, and the red trace is for the L20N module. The purple trace, as it was in our previous graph, is the feed turbidity, and the green line is the flux. So the red and blue lines are our key points of interest on this graph because they represent the performance of the membranes. Throughout the entire length of this trial, the single-ended module operated at a higher TMP. And in fact, the difference in TMP between the two modules closely matched the predicted differences that we showed in a previous slide on lumen pressure drop. So this is good news. Our hypothesis that you could operate overall at a lower pressure for the same flux has shown to be a real outcome. Now the data becomes really interesting in the period of high turbidity. The high turbidity is seen in the later portion of this graph. There was one event at about 43 days into the trial, which continued to another peak after 50 days. One of the first points to note is that the TMP offset between the two modules increased when we faced the higher turbidity. Now, if we zoom in on the high turbidity portion of the graph, we can see that the single-ended unit actually hit the maximum TMP during this period, despite the more conservative flux. But the L20N was able to ride out the high TMP because it was operating at a lower TMP. The graphs represent what the pumps are doing, but what about the aeration? So as I mentioned earlier, the airflow rate was lower per volume of filtrate produced for the double-ended module compared to the single-ended S10N. The difference in flow rates is a 23% savings in air, and in fact, subsequent trials that are not part of the results discussion today have shown that this difference could be even greater. But why would operating in a double-ended configuration improve the aeration efficiency so greatly? Well, the answer lies not so much in the double-ended operation, but in the approach to bringing about the double-ending. Firstly, the fibres are oriented in the same vertical direction as the flow of air as it rises to the surface of the tank. This means that the air doesn't just pass the membrane fibres at one spot, it is kept in contact with the membrane fibres. Secondly, the module design changed only in length. The module diameter didn't change. So you're keeping the air in contact with the fibres longer, but at the same time you haven't made it any harder for any entrained material to get out of the centre of the bundle during a backwash. And you could see that in the previous slide where I showed that the operation remained stable during the high turbidity event. And thirdly, the module shell also keeps the air in close proximity to the membranes. In fact, previous studies have shown, to the point of a patent being granted, that by increasing the amount a module is surrounded by a non-permeable material, or wrapping, the backwash, or more specifically the aeration efficiency, improves measurably. So if you're building a new plant, where are you really going to get the benefit of the improvements I have outlined here? Well, firstly, there is a reduction in footprint. Straight away, because of the 50% increase in area in going from a short to a long L20 module, you get a footprint reduction of about 33% for the module itself. This translates to about a 30% decrease in plant footprint when you take away some of the space to return the filtrate from the bottom end to the top of the tank. In fact, further trials not included today have demonstrated that you can actually take some of the pressure savings as an increase in flux, and therefore you can reduce the number of membranes that you use, which has further potential to reduce footprint. Secondly, the data supports a number of savings in energy, firstly through a reduction in the order of 7 to 20% energy usage for the filtrate pump, depending on how dirty the membrane is, and further significant savings come from the 23% or more savings in air per volume of filtrate produced. And then you've got module replacement costs. So I've concentrated a lot on the performance advantages of a longer module, but I haven't touched too much on the manufacturing implications of this. Both the S10N and L20N have a pod at each end of the module of identical diameter. So really the only difference you have introduced into the manufacturing process is longer fibre and longer screen, so no additional moduling labour. This translates to a cheaper module to make, and this has ramifications both for new systems and for membrane replacement costs through the life of the plant. So you've got footprint reduction, which translates to a reduction in land and building costs, energy savings, which is a significant portion of the operating cost in a membrane plant, and finally, cheaper capital costs at the heart of the system, the membranes themselves. So just to summarise the key points of what we've talked about today, we've shown that submerged systems are worthy of additional industry investment for a number of reasons, but that we need to approach that investment in a responsible way in order to ensure that there is no risk to the end user. So the system I have described today does that by applying application knowledge from both submerged and pressurized systems in taking firstly a proven double-ended module from the pressurized market and then applying well-established operating protocols from the submerged market and using them both in order to minimize risk. And then we've applied double-ended filtration to this combination. So both the theory and the application of double-ending, as well as the use of a simple aerator on module shell, have shown that operating TMPs can be lower, cleaning air is used with greater than 20% efficiency improvement and therefore lower energy costs. And finally, when double-ended filtration allows us to extend the length of a membrane module, we can have smaller footprint plants. So I thank you for listening to the results I have presented to you today and wish you well on your double-ended submerged plant.